record. So yeah, welcome first of all to this seminar, which is with more than 150 participants. It's actually a great seminar to take place. I've never seen such a seminar before. Anyways, so this is organized by Johnny Lundy, Richard Nest, Hang Wang, and myself. So first, maybe some practicalities about this Zoom seminar is that it is probably the best idea to keep yourself mute, unless you have you want to interrupt. But for that, to interrupt, it's probably best to use to raise your hand virtually, which you can do in the corner, which you probably also know. When you click on participants, you raise your hand, and then I will see that, and then I will try to moderate that. Or otherwise, you can use the chat box for that. Yeah, as I said, it's a great pleasure to have this seminar and also to introduce the first speaker, Alain. And that's of course a pleasure for obvious reasons, because it's the field noncommutative geometry that started with him in the early 80s. So in the meanwhile, many things have happened. So the field has really grown to a mature field in mathematics, applications to physics, index theory, number theory, algebraic geometry, and many more. And today we'll see one of them addressed in Quasi-Inner. Actually, it's reversed, Quantized Calculus in Quasi-Inner functions, where actually this first Quantized Calculus is referring back to a concept that was introduced already in the 1980s. So I'm very much looking forward to this. Please enjoy the seminar today. So, Alain.
Well, thanks a lot, Walter. And indeed, I mean, for me, it's a great pleasure, really, to give this inaugural talk for the seminar. And what I will explain something which has to do exactly with the quantized calculus, and which is joint work with Katia Consani. And I mean, the content is a paper that we put on the archive in August of this year, but it also hinges a lot, I mean, as you will see, on a previous paper which we had put, earlier, like in June of the same year. And what I will discuss will be the link precisely between the quantized calculus and number theory. And I mean, the quantized calculus, I want to give you like a very short introduction to it. I mean, and the idea is very, very simple. The idea is the following, is that after all, there is a framework where the calculus, infinitesimals, I mean, many things have their place, and which really comes from quantum mechanics. So the scenery, if you want, the stage is quantum in the sense that you have a Hilbert space around, and that whatever you are considering are sort of realized as operators in Hilbert space. Now, the key equation is the equation that defines a differential. So if you have a function, okay, let's think of it as a function, but it's an operator, and you define its differential by the commutator with an operator f, and this operator f is remarkably simple in the sense that it's a self-adjoint unitary operator of square 1. So it's an operator which is given as twice a projection minus the identity. And the fact that it is of square 1 tells you that when you take twice the differential of a function, you get 0. So you can argue with me, you can say, well, no, what you say is wrong, except that when you take the differential of a 1 form, which is already a differential, you take the graded commutator. So instead of taking f commutator f, you take f t plus tf. And if you do that, you'll find out that because f squared is 1, the iterated commutator is 0. So you can define differential forms. So differential forms are just those operators which can be written as combination of products of 1 forms. And of course, you can put in front a function, but you could also put that function on the right-hand side because it's a bimodule by construction. Now, the beauty of that is that extremely simply and from the very start, you get index formulas. And the simplest index formula is the index formula that gives you, if you want, the winding number of a function on S1 as the trace of the quantized differential of u star is a complex conjugate of this function of modulus 1, times the quantized differential of u. And more generally, when you deal with a space whose dimension is even and not odd, you have to use, as in the Kasparov theory, you have to use a Z2 grading called little gamma. And the formula for the index is, again, very, very simple, because you integrate the differential form by taking the graded trace for even differential forms. So all of that is fairly standard. And if you want to, just to show you, I mean, first of all, let me show you a picture which was the cover of my book, because that picture is telling in the following sense that if you look at the differential, dz equals f commutator z, it's written just, you know, at the level of the neck of the picture. But if you look a little bit more downstairs, what you find is the following. You have to understand this like this. You see, normally when you have a function that, for instance, parameterizes a Julia set or something like that, this by the Riemann mapping theorem, because the Julia set will separate the complex plane into domains, simply connected one, so you can map it to the disk. But the function that maps it to the disk, if you want, or that maps rather the circle to the bound to the Julia set, is a very discontinuous function. I mean, it's a function which is not at all differentiable. It's continuous because it's a German curve, but it's extremely irregular. So if you would take its differential as a distribution, this would make sense. But you would have no way to take its absolute value and raise it to a power, which is not an integer. And even an integer wouldn't do. But here, what you can do, you can take the quantized differential, raise it to a power which is a real number, which is the Hausdorff dimension of the Julia set. And with my Australian collaborators, Sukoshev, Zanin, and their collaborators, I mean, what we have done, we have been able in the recent years to put on a completely rigorous ground what in my book I had described a little bit at the heuristic level, namely the fact that this type of formula does give you the conformal measure on the Julia set, or more generally, if you want, on boundaries of quasi-Fuchsian groups. So, I mean, this calculus has a lot of power. In fact, one should keep in mind constantly to compare this calculus with the ordinary calculus and the calculus of distributions. And what I will explain today is the role of this calculus with respect to the Riemann zeta function. So, I mean, when you take the simplest example of this calculus, you look at functions on the line. So they are just ordinary functions of a real parameter. You view these functions as operators in L2 of the real line. And when you take their commutator with the Hilbert transform, what you find out is that the quantized differential now is no longer just the usual differential, the usual derivative. The derivative is the diagonal values, of course, because it's f of s minus f of t over s minus t up to a normalization factor. But what is really important is that the regularity of the function is actually governing the order of the infinitesimal that you have on the right-hand side, because after all, the differential should be an infinitesimal. And if the function is short space, it's an exercise, which you can prove in several ways, to show that the differential, the quantized differential of the function is an infinitesimal of infinite order. Infinite order means, if you want, what is quite nice with these infinitesimals is that they have an order. So for instance, if you have eigenvalues of the order 1 over n when you go along, then the infinitesimal has order 1. If you have eigenvalues which decay very, 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 very fast, then the infinitesimal has infinite order. And this is the case here. Another very crucial property of this calculus, even in one dimension, is that it is conformally invariant. So by conformally invariant, what I mean is that if I replace the line by the circle, then I will be able to get an isomorphism of calculus from the calculus on the line with the calculus on the circle. Now you could argue with me, okay, but how can you relate the line with the circle? Well, the line is, if you compactify by a single point, it's P1 of R. So, and how do you relate it to the circle? Well, you relate it as domains in the complex plane, which are conformally equivalent. So you see the line as the boundary of the upper half plane, and you see the circle as the boundary of the unit disk. Now, the two things are related by a conformal transformation. You have a little bit to be careful in defining the transformation on the vectors, not on the functions, because on vectors, you want that the inner product of L2 of R transforms into the inner product of L2 of S1. So you have to introduce, something which is like the square root, of the denominator when you take a conformal transformation. The denominator is always a square by construction. So you do that and everything works fine. And then, one proof that if you are in S of R, the differential is of infinite order is that if you are in S of R and you look at the function as a function on P1 of R, then it turns out the function is smooth because at infinity it behaves very well. So when you look at it as a function on S1, it's a smooth function. And when you look at the calculus on S1, because it's related to the complex structure, this calculus, which is given by this F is twice the projection minus 1, where there, the projection will be the projection on the RD space, H2 of the disk. So in fact, it's very easy then. Then it's really a very, very easy exercise to prove that if you have a C-infinity function on S1, its quantized differential is of infinite order. This is just looking at the Fourier coefficients, which have to decay very fast. So all of that is very simple. However, okay, there is one typical feature, which we shall see immediately, of the calculus, which if you would look at ordinary calculus, ordinary differentials, ordinary functions, and so on, would not be transparent, but which become completely transparent with this calculus. And what I want to explain is the fact that we shall have a handle on positivity. So we shall get an immediate handle on positivity of the index, if you want, of the thing which I was explaining before, the trace of U star du. So we shall get this handle because of the fact that when we look at unitary operators, we can ask when is it that in a 2x2 matrix decomposition of an operator, which is typical of what happened in the calculus, in the quantized calculus, what happens if the matrix representing a unitary is triangular? Okay, so I will just state a simple exercise, which you can do in your head, while I'm talking, which is to characterize those 2x2 matrices which form a unitary operator, but which are triangular. Okay, so they have a 0 in the 2-1 place. Now, so it's a very simple exercise to show that this is equivalent to three things. The third one will be on the next page. The first one is that U11 is an isometry. So U11 star U11 is equal to 1. The second is that U22 is a co-isometry. So U22 star is equal to 1. And the third one is that U12, the one which is off the diagonal, it is in fact a partial isometry which goes from the kernel of U22. Remember, U22 is a co-isometry, so it might have a kernel, to the co-kernel of U11. Again, U11 is only an isometry, so it might not be surjective, it has a co-kernel. So the conditions are like this. So they are very, very simple conditions, very simple to check this exercise, but they will play a key role in what we are doing. And the reason why they will play a key role is that when you have such a triangular unitary with respect to the F of the quantized calculus, so you take the F, the F decomposes the Hilbert space into a sum of two Hilbert spaces. So any other operator has a 2x2 matrix decomposition. And now you can ask the condition that it's triangular. Well, if this is so, what you find within 2 minutes, you find that you have a positivity for the index and even a strengthened form of positivity. So the positivity for the index would just be the fact that the trace of UF, U star will be positive. So I prefer to put it in the negative because as we will see later. Okay, so I take my F to be of the form 2 capital P minus 1, and it has a complement which I call curly P. So curly P is just 1 minus P. And now what I state is that there is a negativity fact, which is again very simple to check, which is that the trace of the product of F by what gives the index, namely the logarithmic derivative, if you want, of U, the quantum logarithmic derivative, which is u star f u, will be negative. How do you prove this? Well, it's not much of a problem to prove that the commutator, that u star f u is negative. First of all, you can see that u star f u is self-adjoint because f is self-adjoint, and you conjugate f and you subtract, same. So it's self-adjoint. But then what you find out is that for this projection P, what you have is that u star is less than P. So then by playing around, you find that this operator u star f commutator u is negative. But the product of a positive operator by a negative operator has a negative trace. I mean, we know that, this is something, I mean, the trace of a product of two positive operators is positive. I mean, one should remember that because, it's not only true that the trace of a positive operator is positive. No, the trace of a product of two positive operators is positive. How do you prove it? Well, you take the square, I want to prove that trace of AB is positive. A is positive and B are positive, okay? So what do? I take the square root of A. So I write the trace of AB as a trace of square root of A times B times square root of A, and that's of course positive. So that's done, okay? So that's what we have. We have a fairly general kind of index sign, which is a general fact about triangular unitaries, okay? And I prefer, as I say, to write it as a negative fact. Okay, now, here comes the first crucial point. The first crucial point is that the Riemann conjecture, I mean, RH, is also equivalent to a negativity statement. Or you can say positivity if you like to play around. But, and what is this statement? This statement, I mean, it took us a lot of time to really, not understand, because you can understand a statement. It's a very different thing from having absorbed it. So, I mean, it's a fact that the Riemann hypothesis, even though it's an hypothesis which involves infinitely many primes and which is concerned with the distribution of primes, it turns out to be equivalent to this statement. And in this statement, if you take f to be of compact support, and that suffices. So f is a test function. I will explain where it is and so on. But the key fact is that if f has compact support, the number of primes which are involved in the right-hand side is finite, which is amazing. It's amazing because so this veil equivalence is telling you that even though the Riemann hypothesis is something which involves infinitely many primes, in fact, in order to prove it, you only have to consider finitely many primes at a time. And what do you have to do? And it's in if and only if. So it's not that you are making a bet, that you are going to prove it for finitely many primes and then, okay, fine. No, it's equivalent. There is no way. Okay, and what are these WV? Well, they are given by what are called the explicit formulas, which were certainly known to Riemann. They are called the Riemann veil formulas, but they were, I mean, now in modern terms, of course, okay, you have to explain that they are integrals over the multiplicative group of the periodic fields, QV, which for V, the Archimedean place is just the real line. And then you do an integral. This integral is tricky, and it's tricky for the following reason, that the test function doesn't need to vanish at the point 1. So the integral will sort of diverge at w equals 1, and you have to take in a very careful manner a principal value. So principal values, what does it mean? It means that what you do is you subtract from h a certain choice function that actually has the same value as h at 1, and then you do a little bit of moving around. So, I mean, what I wrote there is integral prime. Okay, I mean, in my paper in 98, I involved a lot on that, but I mean, okay, it's well-defined, but it's well-defined, but you have to be extremely careful when you work with it, because if you would prove positivity for a wrong normalization, you would have done nothing. Okay, so this equivalence of veil is based on what are called the explicit formulas. And these explicit formulas tell you that if you take the sum of the function of the Fourier transform, here it's the Mellin transform, but the two are related. on the zeros of the Riemann zeta function. You put a minus sign in front, you add two boundary values, which are the evaluation at the poles of the complete Riemann zeta function. And then what do you get? You get the sum of the local contributions. And from that, you can infer what I was saying before, namely that RH is equivalent with this negativity statement, okay? So you have this, but now what is the link? Okay, as I said, there is this remarkably striking feature that by the Weil equivalence, you only need to look at finitely many primes. And as I said also, it took years before this statement could sink in. Okay, and once it has sunk in, then you realize that what I had devised in my paper in '98 should play a role. So what did I devise in this paper in Selecta in '98? Well, I had devised a global space, which is the adele class space, and where, okay, one could get spectral realization and so on and so forth. However, this global space had something which was extremely unnatural and delicate. And that was due to the fact that when you look at adeles, okay, the restricted product of the local fields over all places, and when you look at ideals, same thing, but you only look at the invertible elements, then it turns out that when you look at both of them as a group, so you look at adeles as an additive group and at ideals as a multiplicative group, then it turns out that the R measures for these two groups are singular with respect to each other. And that makes things extremely delicate and complicated. But this pathology, if you want, this difficulty does not arise when you take a finite product. And this finite product is not a full adele, but it's only taking a finite number of places, I call S, a finite set of places, which contains the Archimedean place. And I now take the product of the local fields over this set. And I will divide it by what should divide it if it were infinite, and I would divide by the rational numbers, the multiplicative rational numbers. So I divide it by what are the invertible element in a certain ring, which is associated to the set S. And to make things very concrete, let me take S to be given by the Archimedean place and the prime 2. So what would be the ring ZS? Well, it would be the ring of all rational numbers whose denominator is a power of 2. You see, I mean, when you take rational numbers whose denominator is a power of 2, you can add them, you still have a denominator which is a power of 2, and you can multiply them. So you get a ring. Now, in that ring, of course, not every element is invertible. The elements which are invertible are only the powers of 2, plus or minus. So this fact that I mentioned generalizes. And then now we are going to reach the art of noncommutative geometry, because when you divide the product of these local fields, QV, by the multiplicative group of the invertible elements in this ring, ZS, then as soon as you have more than 3 places, let us say, this is a noncommutative space. I mean, you can understand why it's a noncommutative space, because, for instance, if I would divide R cross Q2 cross Q3 by powers of 2 and 3, you will see that the way they act on the real line is dividing the real line by powers of 2 and 3. I mean, of course, this is a noncommutative space, okay? But the amazing fact is that at the level of measure theory, it's not a noncommutative space, okay? In other words, this space XS, as you know, in noncommutative geometry, we always look at a space with several pairs of glasses. And the pair of glass, which is like the coarsest, is measure theory. So in other words, what we do is we take our space and we look at it from the point of view of measure theory, which means that we can neglect sets of measure 0. When we do that, it turns out that this semi-local adele class space is a standard space. Why? Because the measure is carried by the idel. Namely, the measure is carried by those elements in the product of the local fields which correspond to invertible elements, product of the, because the rest is measure 0. The rest is measure 0. You see, if one of the elements is 0, so it's not invertible in the local field, then this will be of measure 0 for the additive R measure. So in fact, what we find, which is totally different from the global aspect, what we find is that in the semi-local aspect, for measure theory is perfect. So the fact that it's perfect from the point of view of measure theory allows us to have a perfect Hilbert space. So the Hilbert space L2 of this quotient space XS, because the measures are the same, I mean, they are equivalent, it makes perfect sense. And it can be defined, okay, you can define the inner product as you would do in the global case, but okay, everything is fine. And it turns out to be canonically isomorphic, but the isomorphism is non-trivial, with the Hilbert space of functions on this semi-local adele class group, which is a group, multiplicative group, and which is the quotient of the invertible elements in adeles, which are the adeles, divided by ZS star. And finally, it's also isomorphic to what you obtain when you take the group CS and you take its Pontryagin dual. Of course, you know, it's always true that if you take L2 of a locally compact group, it's isomorphic to L2 of the Pontryagin dual. So you can do that here. You can do that here. So one should keep in mind that we have three Hilbert spaces. They are isomorphic to each other, but the isomorphisms are very significant and non-trivial. And each time you think about one of them, you have to think in terms of its meaning, and then you will be surprised by the translation. So the thing that plays an absolutely fundamental role is taking place, in fact, in the first one. Because you could say, okay, why do you consider these three, incarnations, you know, these three avatars of the same Hilbert space? Well, when you look at the first one, which is the quotient of adeles by ZS star, it turns out that the Fourier transform defines a unitary in this space. What is the Fourier transform? Well, the Fourier transform, what you do is you take the Fourier transform on each local field QV, and then, because the inner product is sort of dividing by ZS star, you have to prove, this requires a little bit of doing, that the Fourier transform passes to the quotient. Okay, you can prove that. But the Fourier transform is really like, if you want, the tensor product of the Fourier transform at each place. And it's remarkable that it passes to the quotient. Okay, so it passes to the quotient. And when you are in the quotient, then what you can do is you can now play the game of passing from one Hilbert space to the other and understand how it becomes. Okay, now I suppose that I don't have to recall, you know, the work of Tate on the local functional equation. So what Tate did, he showed that, you know, if you consider a local field, so any of the QV, or it could be R, and if you consider Fourier transform in R, let's think about Fourier transform. And I hope I can teach you something which you don't know, but I mean, it's very well known, that if you take Fourier transform, let's say on the real line, then, you know, when you Fourier transform a function rescaled, for instance, by 5 or something, okay? Then you will get the same function as the Fourier transform of the original one, except that you rescale by 1/5, okay? Okay, there is a scaling factor, but let me ignore that. Now, if you think about that, you will reflect and you will say, okay, what does it mean? Well, it means that if I compose my Fourier transform with the inversion of the variable, so I replace the variable x by 1/x. Then what happens is that after all, if I rescale my variable starting from, then in the composition of the inversion with the Fourier transform, I will rescale by the same amount. What does this say for a fundamental algebraist? It says that the scaling group commutes with the inversion composed with Fourier transform. But the scaling group, when we consider the fundamental algebra it generates a maximal abelian fundamental algebra in L2. So if something commutes with the scaling, okay, then it has to be a scaling. Well, not a scaling by a single element, but a scaling by a convolution, by a scaling convolution. So when one applies this, one finds that locally, for each place V, the Fourier transform composed with the inversion is in fact given by a scaling by a certain function. And this function was investigated by Tate And this function is the ratio of the local factors. So now, the miracle, if you want, of the semi-local adele class space is that the same thing holds when you take now the finite product of these local fields, but you divide by this group. Then what happens, again, is that the Fourier transform composed with inversion, okay, is in fact given when you pass to the dual, given by scaling, but in the dual group, the scaling becomes multiplication. So it's a multiplication by a product of terms. Okay, so that's what we have. And I mean, without the semi-local adele class space, what you would get is a single UV, but you would never get their products. So how do you use this product? You use this product because now you can combine it with the quantized calculus, and you get a formula for the Veil explicit formula, which is now expressed in the terms of the quantized calculus. So what is this formula? You have on the second line, you have the terms which intervene with these very precise principal values in the Veil formula. And what do you have on the other side? Well, on the other side, you have the same type of expressions that I was claiming we had a control about the positivity or the negativity before. Namely, it's a trace of the Fourier transform of the function h times the quantized differential. Well, there is a factor of 1/2, okay, fine. And what is this u star, this slash u? It's exactly the expression that I was using for the index. And what is the u? Well, the u is the one that we had before. It is this product of this uv. Okay. Now, so this is, of course, the semi-local trace formula, which I had proved in my paper in '98. But I was always puzzled by the fact that this semi-local trace formula was giving you a sum over places. Why? It was puzzling. It's very puzzling because, after all, you take a product of the QV, the product of the local field. So when you take a product of local fields, you would expect that the trace would give you a product, not a sum. So why does it deliver a sum? Well, it delivers a sum because this u star, this slash u is like a logarithmic derivative. You see, the u is a unitary. And when you take u star, this slash u, you are really taking like a logarithmic derivative. Now, a logarithmic derivative of a product, of course, you have to be careful because things don't commute, but it's fine. I mean, you can play around. And so what you find is that this trace of this product delivers the right formula for Veil, but it has exactly the same aspect as what we had encountered when we were talking about these unitaries, namely, it has exactly the same aspect as this trace of f times u star d slash u, which was negative. So, we are very interested in this in the sense that, well, it seems, I mean, this clearly shows that there is a link between the Veil negativity that we want to prove and type of index formulas that we are very, very familiar with in non-commutative geometry, and that, enter directly when you look at the quantized calculus. Okay, so now, of course, then one would say, okay, well, and this is in fact what I mean, one should have tried from the very beginning, that after all, it could have been that the unitary given by Tate, because after all, we are looking at the product of such unitaries, would be triangular, because we don't have to look at one of them at a time, because it's true that the product of triangular matrices is triangular. So okay, you can look at what happens at, what does it mean that the unitary matrix is triangular for the quantized calculus. And in fact, what you find out is that there is an existing theory, which is due to Berling and to Hardy and several people, which tells you that if you take an element of a function which is in L infinity of S1, which is a unitary, you find that this is what is called an inner function, if and only if the corresponding unitary is triangular in the decomposition of L2 of S1 according to the natural quantized calculus, namely, which has to do with the H2, the Hardy space for the disk, and its orthogonal complement. Okay, so this is a simple exercise. And I recommend to you to look, for instance, in Rudin's book as a theory of inner functions. and understand the link with positivity and all that. I mean, it's all transparent when you think in these terms. Okay, so of course, then you can say, okay, well, I will try to see if at the Archimedean place, which is the first thing that you meet, is it true that this is an inner function? So what is the function? The function is the ratio of local factors according to Tate. And so this ratio of local factor is the following. The local factor at infinity is pi to the power minus z over 2 times gamma of z over 2. And you have to divide by what would be its complex conjugate on the critical line, which amounts to replacing z by 1 minus z. So this is a function. This function, at first, you view it only for the critical line, but you have to view the critical line as a boundary of the half plane, and it's the boundary of the half plane which is located on its left. Now you can compute this function. This function is not difficult to compute, and it's given by the exponential of 2i theta of s, where theta of s is what is called the Riemann-Siegel angular function. This Riemann-Siegel angular function is very important because when you look at the Riemann zeta function on the critical line, it's not a real function. To make it a real function without changing its modulus, you have to multiply it by the exponential of I times theta of s, where theta of s is the Riemann-Siegel angular function. Here you get the double because of what I said before. Well, there might be a sign, but okay. Now, what happens is that when you look at this Riemann-Siegel function, at this graph, you find out that it couldn't be an inner function. The previous couldn't be an inner function because an inner function would have a derivative which is always of the same sign, always positive. So when you look at this function, you find out this is not the case. I mean, Xiangjin, you know, the very good Chinese mathematician, had proposed some idea which was related to this, but I found that it couldn't work because this function is not monotonic. So Xiangjin Li, I mean, you know. So what happens is that then you say, okay, well, this is too bad, you know, we cannot use this triangular unitary and so on. And what we shall see, and this is the topic of my talk today, is that fortunately there is a beautiful theory of quasi-inner functions. And with this theory of quasi-inner functions, I mean, it will repair the fact that this function is not inner. And I will explain that in the two papers with Katia, especially the paper in June, we were able to achieve the goal of proving this Veil positivity for the Archimedean place alone, which of course is very far from the global goal or the goal for finitely many, which would suffice. But however, now we have really, if you want, the fundamental reason why the Veil positivity should hold. And so, I mean, to give you the way that we understood it in the first paper, what we did was, because Katia always insisted that we should have, you know, both the analytic understanding and the geometric understanding. And if you want to get the geometric meaning of the calculations I was doing in 98, you have to translate to geometry by looking not at the operator, but by looking at the Schwarz kernel of this operator. So when you look at what happens in the semi-local trace formula, the operator that enters is the operator which you don't have to understand too much in detail what it is. It is this operator here. Here is a quantized differential, and here is a scaling operator. And you look at the Schwarz kernel of this operator, and you can compute it. It's a very tricky operator. And when you compute it, what you find is, first of all, you find that you can reprove the semi-local trace formula using this operator. Here we are in the Archimedean case. But what you find out something which is rather pictorially obvious, because what happens is that the quantized differential, when you do things geometrically, it is given by the commutator with a projection, but this projection is no longer the Hilbert transform or anything complicated like that. It's just the projection on the elements which are bigger than 1. So when you consider the commutator and you make a change of variables, you find that when you write the commutator, it will ignore the regions which are not in the small square and in the big square. And when you compute what happens with the big square, you find that the Veil positivity, or if you want the thing that you want, is obvious. there, because you can write in terms of a projection and so on. And so the nuisance is the small square. And so when you see that geometrically, you are forced to define what we call the discrepancy. You define the discrepancy. The discrepancy is what is due to the small square, delta. And you can write a formula for this discrepancy. Okay, I mean, you don't have to get lost in the formula, but the discrepancy is something which is a function, actually. It's not even a distribution, it's called delta of rho. And when you define the functional, which is given by this delta of rho, we were able to compute it. This function. And for rho bigger than 1, it is given by an explicit formula. So it's a true function. And the symbol SI that we see here, it's called the sine integral. So it's the integral from 0 to x of sine of x over x dx. Makes sense, because it behaves well at 0. And it's a certain function. You can have it on the computer, I mean, without any problem. And when you plot this function, because this equality with the sine function and so on is only true for rho bigger than 1, but the function is symmetric. If you change rho to rho inverse, it doesn't change. So the graph is of this form. We get a function which has this graph. And it turns out that the peculiar feature of this graph, which is here, plays a dominant role later. Okay. But once you have this function, then you can say, oh my God. Now, what happens is that theoretically, we can prove that if we add to the Weil distribution at the Archimedean place, this new distribution, this new D of F, okay, then it should be positive. All right, what does it mean to be positive? To be positive means that when you pass in Fourier, the Fourier transform is a positive function. That's all it means. So then what we did, we took the computer. With the computer, we computed the Fourier transform of this function, delta of rho, okay? And we tried to see if what we got, adding to it the derivative of the Riemann-Siegel angular function would be positive. Okay, and this is the graph that we got. Okay. I mean, when you see this graph, you see that I called it like the doors of hell or something like that, because look at the value which is here. It's a very small value, and it has to be bigger than 0. And when you make a zoom, okay, to see what happens near 0, this is what you see. So you see that the sum of these two things, the sum of the derivative of the Riemann-Siegel function twice the derivative plus this function is actually positive. But there is better to feel what is going on. You see, the negative aspect of the Riemann-Siegel function gives you this graph. Okay, it gives you a graph which is exactly like this. And now when you look at the Fourier transform of this discrepancy of the function delta of rho, this is the graph that you see. So, which means that this graph is almost cooked up so that it compensates exactly for the negativity of the other one. Okay, so of course, I mean, then of course you have to prove theoretically that the sum is positive and so on. This is done, no problem. And then you have to control this function delta of rho. Now, what we proved in the paper in June with Katja is that when you look at this function delta of rho, it's in fact related to the quantum cell, namely to something which I had defined in my paper in 98, which is the cutoff projection for the value of the cutoff, which is 1. And so for rho bigger than 1, this delta of rho, this discrepancy, is in fact just the trace of scaling multiplied by p at p, where p is a projection on this, cutoff projection, and p at is a Fourier transform. Okay. So then, if you want, there is a work, quite a work, which is done, which we did in that paper, which is the following, which is that when you have a pair of projections in Hilbert space, well, you feel very well, because a pair of projection is the same thing as a representation of the diedral group. And representations of diedral groups, they are given by just the irreducible representations are given by an angle. And moreover, for this cutoff projections in the Selecta paper, I had used the theory which was known, which is a theory which is due to Slepian and several other people, which allows you to compute this angle and to compute the eigenvalues. So it allows you to understand the situation. But in the situation, there is something amazing which happens, which is that when you look at these two projections, P and P hat, okay, in L2 of R, so let's take even functions. So P is a projection on functions which have support between -1 and 1, and P hat is the Fourier transform. Now, it turns out that it's not true that P and P hat generates the whole Hilbert space. There is a subspace which is orthogonal to both P and P hat. This subspace is well known. It's called the Sonin space. And this Sonin space is formed of L2 functions which vanish identically on -1, 1, and whose Fourier transform also vanishes identically on -1, 1. And it's infinite dimensional. Okay, so you look, and what do you find? You find that in fact, this Sonin space was perfectly there already in the decomposition of this local factor U infinity in the splitting of the quantized calculus. Namely, it turns out that this Sonin space is just the kernel of the U22. So I remind you that if we had had a triangular operator, the kernel of U22 would have been a key because U22 would have been a co-isometry. And this kernel here, it turns out this is a simple exercise that this is exactly the Sonin space. And what we proved with Katia in the June paper is that in fact there is a much stronger form of the veil positivity. And this much stronger form of the veil positivity tells you that when you take the veil functional, which you want to prove to be positive, and when you evaluate it on the positive element, G star, then it turns out to be larger, I mean, under some boundary condition, than the trace of theta of G times the Sonin projection times theta of G star. And of course, the right-hand side is obviously positive. But the moral of the story is that the root of the veil positivity is given by the Sonin space. Okay. So,
Alain, there's a question.
Yeah.
Peter Ivankov. You can ask your question.
Yeah, sure. Yeah, what is the question? Well, if I cannot hear the question, I will answer.
Yeah, sure.
Okay, so let me continue. Okay, so I mean, I don't want to spend time because I have little time left, but you see what happens is that the proof of this inequality is very, very involved in the sense that the first thing that you do is, as I said before, you know, you use the pair of projections to move the little square delta inside the big square, and then you find that what remains is this Sonin space. And then when you work with what remains, you have to prove the inequality, and to prove the inequality, what you do is you use a technique which has a lot of conceptual meaning, which is that you replace R plus star first by discretizing it, by replacing by Q to the power Z when Q, and you let Q tend to 1 plus. Now, of course, this is the story, you know, of FQ tending to F1 and so on. But then what you find out is that you can approximate the operator that you don't know by an approximating operator which depends on Q, but which happens to be a Toeplitz matrix. Now, by a great fortune, at the time when we were doing that with Katia, I was collaborating with Walter, you know, on generalizing the non-commutative geometry to a much broader setup of operator spaces and so on. And we are focusing in particular on Toeplitz matrices. So I learned the theory of Toeplitz matrices just at that time. And it turned out that this theory of Toeplitz matrices was sort of tailor-made to apply in our case with Katia, which is that we were able, thanks to this general theory of Toeplitz matrix, to guess from the case of Q tending to 1, what was the closed form of an operator that would actually would be of finite rank and which was a perfect approximation to the operator K. I mean, what I should say also as far as the virtues of the quantized calculus and so on and so forth is concerned, is that the role of delta is a small, it's like an infinitesimal difference between veil and something which we know to be positive. So the idea that compact operators are infinitesimals plays a crucial role here, because you say, well, okay, you know, if this delta, if this small discrepancy and so on would be 0, we would be done. We are not done, but we are dealing with something compact. Okay, so I mean, I don't want to evolve on that, But then what we found out, if you want, so yes, I should say just one word on the theory of Toeplitz matrices that should tell you a lot, which is that there is a kind of baby version of RH for Toeplitz matrices, which is the following. If you take a self-adjoint Toeplitz matrix, and if you take its largest eigenvalue, well, assume it's isolated, then it turns out that there is an associated polynomial to the vector which represents this largest eigenvalue. And it's a general theorem, amazing, that all the zeros of these polynomials are of modulus 1. So this is a fact which we used in our work with Katja to approximate, to find the limit when q tends to 1 and so on and so forth. But if you want, the main thing that we discovered can be encapsulated in a general definition. What we found is that, in fact, even though this unitary, u infinity, is not an inner function, it is a quasi-inner function in the following sense. In the sense that when you look at the corresponding matrix, unitary matrix, it's not triangular. But when you look in the Calkin algebra, it becomes triangular. Now, so I mean, in terms, if you know operators, this is saying that the corresponding Henkel operator is compact. That's equivalent to saying that. Now, you know, of course, that function couldn't be inner. And it couldn't be inner because it's given by this formula. And when you look at this formula, the function has many poles in the place where it should be holomorphic. So it cannot be an inner function. It's not holomorphic. But if you work on it, if you work sufficiently on it, then you find out that you can use the Cauchy formula if you want to compute the negative Fourier coefficients that normally should be 0 if it were inner. So you do that. You use the Cauchy formula to compute these Fourier coefficients, okay? And with the help of this Cauchy formula, what you find is that there is a beautiful expression, closed expression, for the part that should be 0 if the function was inner. And look at this formula for this operator. I mean, so the operator is 1 minus p kappa. Kappa is because I change variable times p. But look at the sum. I mean, on the right-hand side, you have a rank 1 operator, which is the Dirac Bra-Ket, if you want, for xi(n) and eta n, which are both unit vectors. But look at the coefficient. The coefficient is tending to 0 at a fantastic speed, because it's like 1 over gamma times gamma. Okay, it's the product of two gamma functions. So this tells you that not only it's an infinitesimal, I mean, it could have been an infinitesimal decaying like an exponential. No, it's an incredibly faster infinitesimal. It's microscopic. It's almost nothing. Okay, so now the question arises, and okay, I'm reaching the end, but the question arises, what happens? So, okay, yes, by the way, I just want to mention that there are general theories of Henkel operators and so on, and that we are able to decompose this function as a sum of smooth function and a holomorphic function. But okay, this is a side remark. And okay, it has a certain form. Now, the obvious questions are, okay, but what you have done is only for the Archimedean place. So what happens in the semi-local case? And there are two obvious questions. The first question, of course, the projection P and P hat, they continue to exist. The first question is it still true that the angle operator between the projections P and P hat is compact? Because if it is true, then you will be able to imitate the method which was used in the Archimedean case. And the second question, well, there is an obvious analog of Sonin space, which is that you can take functions in L2 of XS, which vanish in the unit interval. But okay, the unit interval is a little bit more delicate to define. You have to use the modulus. And with Fourier transform also vanish there. But is it true that this space is infinite dimensional? You have these two questions. They are there in front of you. Okay. And what we proved with Katja, so by the way, so the local factors at primes are much simpler than the local factor at the Archimedean place. They are given by this formula, okay? And the theorem that we proved with Katja, we proved that if you take a local factor at a prime, it's not true that this function is quasi-inner. So that's, you know, when you see that, you say, oh my God, they are going to spoil everything. No, they don't. Because when you take their product by the local factor at infinity, so if you take the product of the local factor at infinity by a finite number of local factors, of ratio of local factors at finite places, then this is quasi-inner. And the way this is proved, it's very tricky. It's very tricky because the non-commutativity of the space is entering. The way it enters is as soon as you have 2 primes. If you have 1 prime, fine, no problem. But when you get 2 primes, what happens is that when you look at the poles, the fact that powers of 2 can be the same or very close to powers of 3, you know that 2 to the power 19 is almost 3 to the power 12, then this enters to spoil everything when you try to make a sum over the poles. So, so the way we proved it, we use the Gauss multiplication theorem to factor the Archimedean ratio rho infinity into a product of m quasi-inner functions, which are very much the same taste as what you get for rho infinity. And then we distribute this quasi-inner function with each of the prime. And because the product of quasi-inner functions is still quasi-inner, we get the result. So I will finish with the 2 statements. So the first statement is that, you know, as I said, there is an obvious definition of the semi-local zone in space. But it turns out that this semi-local zone in space is simply the kernel of the 2-2 part of the quasi-inner function, which is given by this product. Remember that if the unitary had been triangular, then the 2-2 part would have been a co-isometry. So now it's only quasi, if you want like that, but still we can look at this US 2-2, and this turns out to be the semi-local analog of zone in space. But now the question arises, okay, this is fine, but is this space infinite dimensional? This is not obvious at all. I mean, you know, because if the function was, if the unitary was triangular, yes, but it's only triangular in the Calkin algebra. So is it true that this kernel of US22 is infinite dimensional? And so I will finish on that. I mean, that's what we found during this summer. And it turns out that there is a remarkable map which turns the Sonian spaces defined as above into a colimit, into an inductive system. And the injective linear map, which goes when you enhance the set of places, for instance, if you had 1 prime, okay, then it turns out that there is a kind of completely obvious map, which turns out to map the Sonian space for S to the Sonian space for the enhanced S prime. And this map is simply multiplication by the product of 1 minus p to the minus z. I mean, these are not the local factors, they are the inverse of the local factors for the elements which don't belong to S, but belong to S prime. Okay. And so if you want, now we are in the situation with Katya in which our task is to be able to do for the semi-local case what we did for the local case. We are not saying, you know, that it's doable. It will be certainly very hard, but somehow we have the analytical ingredients ready for that. And what we plan to do is to put into action the geometric part. The geometric part, which was so valuable in the case of the Archimedean place, because it gave us the little square and the big square, and it gave us, if you want, the understanding of the discrepancy and the control of the discrepancy and so on and so forth. But I hope that I gave you a taste of, you know, the fact that the quantized calculus, even though, you know, one could try to reduce it to the ordinary calculus, no, it's much more powerful. And I mean, and there is an incredible tight link between this calculus and the veil problem, just because the formula for the veil functionals and so on, it can be so simply and directly expressed in terms of the quantized calculus. Okay, so I will end here.
Thank you. That's a virtual applause or a real applause. Okay, so thank you very much.
Yeah.
So now time for some questions, if there are. So there were already some hands waved at some point. Maybe there was a mistake, I don't know. But if there's anyone who would like to ask a question, now's the time.
I hope my rhythm was not too fast, but it could be. Yes.
Maybe to get started, so can you give a feeling of what quasi-inner would mean if you look at the function itself? Because now it's
yeah,
you translate it in terms of compactness.
Sure. Yeah, so I mean, what it means, if you want, is the following. What it means is that, you see, the function is not holomorphic inside the disk, okay? However, what it means, and let me come back to one of the results which I passed very quickly. Yes, you see, so the meaning for this function, which corresponds to the infinite place, is that the function is not in H infinity, so it's not holomorphic, but it is the sum of a holomorphic function with a smooth function. That would mean that, that would imply that it's quasi-inner. Now, smooth is too much to ask, because then the infinitesimal that you get is of infinite order. So, I mean, in the case of when you add primes, you don't get an infinitesimal of infinite order. You get an infinitesimal of order, which is 1 over 2m, where m is the number of places that the number of primes you have added. But so the feeling is the following. You see, when you consider this function, the Riemann-Siegel function, theta of s, you could say, oh, well, okay, this function is smooth. Well, except that you are looking at this function on the real line, and you want to compactify the real line into P1 of R. So the way this function oscillates at infinity makes it not smooth at all. You see, so I mean, let me see where it is, this function. Yeah. Yes, so you see this function, when you take exponential I theta of s, I mean, what it means is that if you look at it at infinity by a conformal transformation, it will terribly oscillate at infinity. And these oscillations, they correspond to the number of zeros of zeta. So you would say, well, it's impossible. This function, you know, cannot be smooth on P1 of R. But the theorem is that if you subtract from it a holomorphic function, then it is smooth. Mm-hmm. And that's an amazing fact. You know, and that's what we understood. And I mean, we understood through a number of very strange steps, because, you know, as I said, at the first, there was this guy, Xianjin Li, who had a very good idea, but his idea couldn't work because of this graph. So then, you know, then we started thinking about it and so on. And gradually, I think we see a lot. I don't think we see all, but you know, at least the strategy is completely clear now. I mean, the strategy is that the root of the veil positivity is like an index formula. It's a fact that there is a matrix which is not triangular, but it's quasi-triangular. And the fact that it's not triangular, but quasi-triangular tells you that you have to take into account the discrepancy, and you have to understand this discrepancy. So we did the work of understanding this discrepancy for the Archimedean place. What remains to be done is to see if the similar work can be done for the finite places. And you know, that's the task. But I think it will involve a lot of computer aid, because I mean, the papers that we put in June was involving computations, which each of them was taking 3 days of computer work. You know. So I mean, it was really quite tricky and involved. I mean, at that level. So of course, I mean, with the primes, it will be even more involved. I mean, this is clear. But on the other hand, okay, we are so lucky to have the computers. When you think, you know, at the time of Riemann, they had to compute by hand. So I mean, now we have no excuse. I mean, we really have to use the computer. I mean, just to understand what is going on.
There was also a question. I'm not sure if that was a question of Ali Tagavi.
Yeah.
That, if you want, you can ask your question. Yes, go ahead. So unmute.
I don't see.
So can you ask a question, Ali?
Yeah, well, I don't see him. I don't see the, yeah. Ali Tagavi, yes. No. I see, like saying, yeah. Yeah, well, okay. I mean, you know, these things, of course, they take time to digest. I mean, but I think the message, the general message should be very clear. You see, the general message is that the formula of veil can be written as an index, I mean, with an F in front. And moreover, you know, it's, I mean, the sort of, you know, it's begging for the understanding with quasi-triangular or with this stuff. I mean, you know, it's, and the thing which is behind everything is the Fourier transform. So if you want what is remarkable is that you could put by hand the product of the ratio of local factors, but then you could go nowhere because you wouldn't know it comes from the Fourier transform in the semi-local case, which is where things happen. And this is what gives you the primes and what gives you exactly the Weil formula with the right place where primes enter with the normalization and so on. I mean, you know, so I mean, it's not an arbitrary formula. You know, it's a formula where you have to put all the primes where they enter and so on. This is very clear.
So maybe I can, so I have the question of, it's
Yes.
in the chat. So the question is, what is the definition of angle operator between two projections?
Okay, so let me explain that. Yes. So you see, if you have two projections, let me call them P and Q, okay, with capital. Then what happens is that in fact you have two unitaries of square one, because 2P minus 1 and 2Q minus 1, I call them U and V. They are unitaries and they are of square 1. So in fact, what I have a diagonal group, because if I form words with U and V, I cannot repeat U, I cannot repeat V. So these words, they will be like UV, UV, UV. Perhaps there will be a U at the start or a V at the start, but this is a semi-direct product of Z by the involution. Now, when you take a group which is a semi-direct product of Z by the involution, turns out that by the Mackey theory of induced representations, the irreducible representations are formed just by 2x2 matrices and two subspaces of C2, but you can in fact reduce to R2. So what you have is two subspaces of R2. One will be the x-axis. The other will be another axis, okay, another line going through 0. And in the irreducible representation, the projection P will go to the projection on the x-axis, and the projection Q will go to the projection on the other line. Now, when you are in that situation, the angle is obvious. I mean, it's the angle between the x-axis and the other line, okay? But because you know what is the angle in the case of an irreducible representation, and because the group is of type 1, so any representation of the group is a direct integral of irreducible representations, okay? So then you know what is the angle operator. I mean, it's just what I said before for each irreducible, which you integrate when you take an arbitrary representation. So as I said, you know, a pair of projection is just a representation of the diagonal group. And from what I just said, it generates an operator. Now, this operator can be computed concretely. The cosine square of the angle is something like the absolute value of P minus Q square, or perhaps the sine square. It's probably the sine square, yes. So you can give a formula, but what is remarkable is that, you know, for the operators we are interested in, the angle will be discrete. So the angle will just take a discrete set of values, plus the fact that if the orthogonal of these two projections is infinite dimensional, then of course the angle has infinite multiplicity. And this is the Sonin space. So if you want, it's a beautiful situation. I mean, you have the Sonin space, which is the root of positivity, and then you have where the angle is non-zero. But this you can analyze. And I mean, of course, this analysis has now to be done in the semi-local case. That's really what, but at least you know that it's a discrete set of values because the angle is compact. Okay, right. I mean, in the two papers, you can find all sorts of details. I mean, you know, I was, of course, not able to give the details. I mean, but and sometimes they can be very, very complicated. I mean, for the business of the prolate functions and all that, they are very, very complicated. But on the other hand, we have the computer, so that helps a lot, actually.
All right. So okay. Thank you.
Okay.
And if there are no further comments or questions, then well, thanks again for opening the seminar, and
okay,
I'll see you.
Great. Yes.
See you next week.
Okay. So bye bye. Thanks a lot.
Bye bye.
Yeah.
Thanks.
Hey, Alain.